Hello, my name is Peter Luisi. This is my presentation for Foundation of Computer Science. And your UMass low number is 014999304. Let's get started. When my first thing I ever done for Foundation of Computer Science is 1.1 because I received the book from Amazon 1 week before the paper, so I wanted to get the motion down to how to draw uh, a machine and also how to identify a machine. That's what 1.1 and 1.5 is for. For 1.1, as you can see, I wanted to know what was the start state, the accept state, and how would it go through input. I just gonna for how short this video will be. I would just be going over M2 since it's more complex. For how I label the start state is labeled by the arrow because for machine that's how it's labeled when on the diagram, and that will be Q1 for M2. For substates is visual drawn as two circles inside each other. One that for M2 that be Q1 and Q4, and then for C, if it reads the input AABB, M2 would first be in Q1 since that would be the start state, then reads a A, go to Q1 again because it loops, Q1 again because it reads another A, then go to Q2 because it reads B, and then go to Q4 because it reads another B, which if it's in Q4, if that B input keep continue, it keep being B, it keep being Q4. And since it's in Q4, it'll be an SF state. And then for E, it asks for if I accept an empty string, would M2 be in the accept state? Yes, it would be because the start state would be in Q1. This was a test to see how I'm able to see see the difference between a start state, a accept state, and how to go through inputs. 1.5 was mostly how if I'm giving a bit of information, will I be able to draw machine, some sort of machine. Like, and what I found out, it came in handy during the first exam because then I had the vending machine problem, and even though that vending machine problem was fun, I did that last, and it allowed my mind to go through. It seems like I can like read every sort of input from how a vending machine goes through, from going seeing if it gets the right change to get the roll and number, and if it got the can and seeing how it goes to accepts and rejects. Since this video is short, let's go to a more media problem that other than my 1.1 1.5 was really the basics for me to get into this class. 1.11 was me trying to understand what is an NFA for, because since NFAs can be turned to a DFA, but NFA is able to clone itself. The 1.11 is questioning if I can put all those accept states if NFA has multiple accept states into one single accept state, and I say yes. Since NFA can clone itself, it can branch off, and at a node can, I believe, can accept multiple different inputs, as in like different inputs can be able to go to that state. So since NFA is able to clone itself, it can have multiple opportunities to go to that state, and that state can also branch off to multiple states too if it reads another input. Since NFA can also clone itself, it can go out of that substate if it reads another input to lead out of that state. So I said yes, it can go to that SS state in one fell swoop. I don't know, visually drawing it's fine to visually draw. You just have like multiple states of all readings, different inputs, and going to this SF state, and this SF state can be able to stop there, loop there for some of the future inputs, or go to different states. Next, let's go to chapter 2. Which was about context-free grammar. What my most difficult thing to think about was 2.24 because I don't know if proving, like visually proving that the 2.24 was about if for the following G, we'll be able to show that the language if there was an equal number of A's and B's. So I don't know. So I also gave an expression. It was somewhat of a test for what you said. You may have a question about proving, like showing how to prove if some language is equal on, that you can actually show to prove that language. So I did this as a mock exam practice to see if I'm able to label it, and then I didn't really have a lot to say about it. I just had to visually show like some input, some form of n that could happen, and then I had to and then show for if I go one step further from proof of induction. I'm pretty sure I just need. My thought process was to go one step further, like I read the T's as they should be, because the rule for this question is S goes to T, and then goes to either goes to TA TB or TB TA or the empty string. Another thing that I found challenging for this chapter was 2.14, mostly because I'm still having trouble with Chomsky's form. I'm not a very good question person. So if you have the time after this presentation, like see if that is Chomsky's form for me. Like how can I write it in Chomsky's form? Because I don't know if I have to do this in future classes, and having this down may help me. And mostly for when we went over in class for chapter 2 for context-free grammar, my mind was still fuzzled because my mind was still fuzzled there for what is a context-free grammar and what is not. I could make a definition for it. Give me a problem to definition for it. Allow me to write it out. It's fine. But for proving it, I'm still having trouble in it. Even as now, I take that into account to the final. For as you can see with 2.13, I don't know if it's that because 2.13, if I'm remembering correctly, let me go back to that page. Describe, at least in this one, it's describing a language, which if I can make a string, using the rules, it should be a language. I don't know if I'm using it correctly, if I can pronounce it correctly or explain it correctly. Like for B, the string can, for B is to prove that LG is not regular. I don't know exactly how to prove that. I don't know if I explained it correctly, but A is like, can I describe LG in English? It's for how to say is like, can you make a string out of it? Like I can make a string could be TT, and it could be either at the end result or U, and the end result could be either one symbol or like some number of zeros in the front and zeros in the back for in between the symbol, or 0U. Or it could be odd number of zeros in the left and even number of zeros to the right, or mixed match. But right, most likely if it goes to the U for the 0U00, there's gonna be more zeros to the right than zeros to the left. Let's go to chapter 3. As I know, first I forgot 2.31 and 2.33. These ones have got my mind thinking. So let's see if I can go. There was another form of describing a CFG, which once again I think I did this later in the class, and I think I did a better form of explaining what a context. If this is a context-free grammar, because it actually has a language. I can actually not actually has a language, but I can actually show the language. And I took 2 different counts on it, and like how to explain it. I don't know which one's better, in 2.31 or in 2.13, but I believe 2.31 has a better understanding. Like I had a better understanding. Then 2.33, and if I'm given a CFG, generate the language of strings with twice as many A's and B's and prove that your grammar is correct. So I basically made the rule of like one rule that if you like this is like if in the beginning you only had S, your starting variable would be S, and then your alphabet basically would be A and B. Your rule, you only have 2 rules really. The one rule is every time you see a S, you print out an even number 2 A's with 1 B, and then if you read an empty, you have 2 A's, 1 B, and then The reason why I did this because there's always has to be a double non A's and odd number B's, so I'm pretty sure that just an empty string will prove this wrong. So that's why since you're starting an S, it either way it goes to a 2-to-1 ratio. For every 2 A's is 1 B, so either way it should be able to I it should be the amount of B's is half of the amount of A's, and I believe that's how I can prove it. I don't know how can I prove that this grammar is correct any other ways than visually showing it or explaining it. That for the 2-to-1 ratio, but I believe this is enough. Next off, we don't have no much time. Next off, we go to chapter 3 about turning machines. This turning machines is so far in the class when I really liked about the topic of foundation computer science, because everything else I felt so a little fuzzy. Let's see. And 3.11 it showed like a string showed that the tape containing the input string recognizes only regular languages. I just explained it that the string won't be like the tape won't be able to read anything from the input if it won't count as a regular languages because it could go through a loop. And also I took it on as like stating if that the tape and the input are not together and that they're separate from each other, because since those two have different alphabets, they take their output differently for different inputs. I believe that's how I explained it. That's still really for regular languages. For recognizable languages, for this is talking about how if there's an infinite number of recognizable languages, there's an infinite number of subsets, decidable subsets. For decidable for a turning machine. A decidable is when the turning machine for that set has an end, that it does not loop and does not go to reject. And since these sets that the turning machine takes are infinite, that means there's always these decidables can go higher for a set. Like another set can use this set for a subset or use this set as a reference. So it can like this. Think of it like a Russian doll, like in reverse. Like other than you taking out, you start with the smallest Russian doll, and it just gets bigger and bigger and bigger. And also that small Russian doll can also be a set. Is a set, but something can be a subset of that set. So it come out. It's just like a weird Russian doll. Where do you start? It goes bigger or goes smaller. Either way, I believe it's an infinite loop. For infinite, it's just infinite. I don't know why I say infinite loop. So it does not really have an end. Oh well, everything has an end, but it's not something we tangibly can take. And let's see. Next question, 3.21. So talking about a queue. With this question is talking about if a queue that works like a push-down automata is a turning machine. For how it works like a push-down automata, it can push and pull depending on what it reads, but just in tape form, and that it will only accept. Show that a language can only be that is recognized by it will only recognize a language if and only if a turning machine is recognized by a turning machine. The reason why I take it as in this is that Q is like a more not really complex, as in it's just harder to do its process. It's just that it takes more steps to do its process because all the push and pulls, which a turning machine can do this in one fell swoop, because it can replace the symbol that it's in. But for a queue, it reads from the right, but if it needs to take anything, it takes from the left. And a pull, which is like a pop function, it takes away the symbol on the left, but it has to read from the right. While the turning machine can read both from what it points to, take it out, and replace it with something. So my thought is like anything a turning machine anything a queue can accept, a time machine also accepts. So anything, so it's like how any NFA can be a DFA. That was my thought process on this. And all these questions have been challenging for me because one is one of my thoughts of going to class in everyday classes. I write down the notes, get the ideas flowing in my head, and then make the ideas founded, have a foundation for these ideas in the book. All in all, these are my ideas for how to do these questions for chapters 4.1, 4.2, and 5.1 and 5.3. I've tried these problems, but I still having problem and found making these ideas founded and have a foundation of it. So I chose not to include them into my presentation. If there's any questions, any concerns, please contact me. Thank you very much.